Hey everyone, it's Pranav here, and welcome back to Pranav's Tech Tips. Yeah, it's been a while. The YouTube algorithm may have moved on, but my GPU definitely hasn't. So, for this comeback video, we'll be diving into something really exciting in the deep learning world. Triton, a language and a compiler for deep learning primitives on the GPU. In this video, I'll be deconstructing the Triton repository, highlighting the overall architecture, and finally running a sample Triton program and benchmarking it against PyTorch to see how it performs in practice. So, if you ever wanted to create a custom fused operation in PyTorch or looked at CUDA and thought, this is powerful, but mildly terrifying, then stick around. This one's right for you. So, what is Triton? Triton is an open source programming language and a compiler from OpenAI that lets you write high performance GPU kernels in Python. There's a lot of magic involved in here. So, we write our kernels using Python, and then Triton helps us to compile this into GPU code. And finally, we get performances close to hand optimized CUDA C++ codes without digging deep into C++ or the GPU intrinsics. So let's consider Triton as a CUDA level performance and a Python level ergonomics language. So, why do we need Triton? Before Triton, we basically had two extremes. The first one was high productivity PyTorch or TensorFlow framework. This was super easy to write as it was written in Python and had great performance for standard built-in operations. But the moment we wanted a custom fused operation or a new primitive, we usually end up chaining multiple kernels. This means we had to take more trips to the global memory and had more memory traffic and ultimately worse performance. The second one was high performance CUDA C++ language. We get maximum control and maximum speed, but it's a bit hard to learn and hard to debug. And pretty sure it is very much painful to maintain, especially for fast moving research. So, Triton was designed to bridge this gap. We still could control things like tiling, memory layout, and data movement. But we do this in Python, which is less complex than raw CUDA. So instead of choosing between fast but painful or easy but kinda slow, Triton aims for fast and still pleasant to develop with environment. Alright, let's now look into the Triton repository and get an overall view of the architecture. So for this purpose, we'll be using the most recent agent-based coding IDE. Any guesses? Yes, it is the anti-gravity IDE from Google. It looks like a standard code editor, but it is actually designed to let AI agents take control of the development process. So instead of just auto-completing the entire lines of code, these agents can help you plan tasks, execute commands, debug issues, and even verify changes across the terminal and the editors. I'll be posting an upcoming video where we'll go through the anti-gravity itself and really test its limits. For now, let's just dive into the Triton's architecture. So, this will be the entire pipeline diagram of the Triton workflow. Let's think of this as a little journey our code goes on, starting as a plain Python text and ending up as a highly tuned GPU kernel. Let's just follow that step by step. So, we begin at the very top with us in our code editors writing a normal Python code. We import the triton.language package to write our kernel functions and add that little triton.jit decorator on top. At this point, it just feels like we are writing a regular Python function that happens to magically run on the GPU. So this would be our starting point. As soon as we call that function, the Triton frontend quietly wakes up in the background. It takes our Python code and turns it into something called the abstract syntax tree, which is basically a structured representation of our Python code. From there, the Triton converts it into something called the Triton IR, which is basically Triton's own internal language, and it talks in the terms of tensors and blocks. This Triton IR is basically built on the top of MLIR, which is otherwise called the multi-level intermediate representation. This is the moment where Triton stops to see our code as just Python text and starts seeing as a kernel where it can reason about and optimize. So next, our kernel will be moving into the optimizer stage, where the TTIR is basically massaged, improved, and transformed into something called the Triton GPU IR, which is more closely aligned with how GPUs actually operate in the environment. So from the GPU IR, the Triton basically lowers down everything into something called the LLVM IR, which is low level machine virtual machine IR. So by now, basically our kernel will have gone through from very high level tensor world into a low level hardware agnostic representation that the LLVM toolchain understands. So now basically we'll be arriving at our backend where the LLVM IR gets turned into real target specific GPU code. So for example, if you are using an NVIDIA GPU, it will be converted into a PTX format. Whereas if you are using an AMD GPU, we'll be having something called the AMD GCL. So here the Triton is essentially saying, okay, I now get exactly what the GPU we are targeting, and let me speak with the GPU in its native language. This is where the final GPU instructions are basically generated. After which, we finally arrive at our GPU runtime, where the Triton's runtime and the kernel launcher takes this GPU compiled GPU code and talks to the CUDA or the ROCm driver. Here, the kernel is basically loaded onto the GPU and the launch configuration is set up and the kernel is executed. So, this will be the mental model which we will be carrying with us as we dig deeper into the Triton's repository. And later, we'll be running a sample Triton program and benchmark it against PyTorch and see how all of this theory plays out in practice. So now that we have seen the big picture pipeline, let's zoom into the very first layer, the part where we actually touch as developers. For this explanation, we are going to use the sample matrix multiplication kernel, which was actually generated by the anti-gravity agent. We'll use this one example to follow the entire workflow end to end. We'll start our code with a couple of imports. First one is the import Triton, which brings in the main Triton package into our code. Following that, we'll be importing the Triton.language as TL, which loads the Triton DSL. This TL namespace is basically the Triton's view of the world. All the primitives which we will be using inside the kernel lives here. Alright, let's now move into our Triton kernel. So if we scroll down a little bit, we'll be able to find the Triton.jit decorator. So this decorator is basically our entry ticket into the Triton compiler. The Triton decorator basically tells that when this function is basically called, don't just run the Python code, but compile this into a GPU kernel and launch it on the device. So from here onward, we'll be no longer writing just regular Python code. We are going to define something which will ultimately become the GPU's machine code. Now, if we go a further bit down, we'll be able to see expressions like block size of m with a TL constant expression and followed by all the others defined as TL constant expressions. So this is basically saying that these values will be known at the compile time to the Triton. So the TL constant expression annotation basically gives Triton permission to be very aggressive with the optimization. Now, if we peek behind the curtain into the Triton source, we can see how this DSL actually works. For this, we'll be going through the core.py function file, which is basically the heart of the Triton and Python's DSL. So we can find the built-in decorator, which is basically telling the Triton that it is not a Python function, but a part of the Triton language itself. So this function basically is having some Python object x, which we want to interpret as a tensor. And it also has a handler that knows how to convert this Triton's how to convert this particular object into Triton's internal representation. So inside, it basically calls semantic.toTensor of x. So instead of it really doing the work, it delegates it to the compiler's semantic layer. So in other words, we can say that when we pass something into the Triton's DSL that needs to be treated as a tensor, this particular hook helps the Triton say that it knows how to convert it into its internal tensor representation inside the IR. Next, we'll be able to see the constant expression type which we used for defining the block sizes. So this is basically the Triton's way of actually saying that it knows the values before running the kernels. So when we write the Python statements like say block size of is equal to tl.constant expression, what we are exactly telling the compiler is the block size will never change in the compiler will never change in the kernel when it's executing. So the compiler can safely unroll loops, specialize coding paths, and also pre-compute offsets based on these values. So at the front end, basically, we are writing an entire clean code using Python, but every import, every built-in, and every tl.const expression operator helps the Triton to translate our code into something that a compiler can optimize very aggressively. Once our kernel leaves the front end, the Triton stops to think the Python syntax and starts to think as its own internal language. That's where we have two IR stages that come in. One is the TTIR, which is a tensor and a block level IR, which is great for expressing high level GPU bands. The other one is the TTGIR, which is more GPU oriented IR and is closer to what the hardware wants. We can just see all these implementations done in this particular C++ file over here. In this file, let us look at one of the most key operations, which is the load operation. So it is basically the Triton IR's level of read from memory operation. Basically, this is what our code, where we have the tl.load function actually does. So it loads a block of values from the global memory and applies masks, boundary checks in order to avoid out of bound reads and fills in invalid lanes with other values. And it can also have cache or eviction hints for performances. So basically, this single line of code becomes a fully described load operation IR in something that the optimizer can basically reload, refuse, and also improvise. So that is basically the bridge between the friendly Python to how it gets converted into the compiler grade IR. So after the Triton optimizes the Triton IR and the Triton GPU IR, it lowers down everything into the LLVM IR, which is a low-level type representation used as a common compiler target. We can see the entire lowering logic over here in this particular element-wise operation to LLVM C++ file. So let us see how the Triton's add operation pointer becomes the LLVM get elementary operator pointer. So here what happens is it basically takes the Triton's base pointer and applies some offset, and finally the LLVM turns it into a type pointer arithmetic instruction. And this eventually becomes the real GPU's machine code. So even though we think in the terms of blocks, tiles and tensors in Python, Triton quietly converts this into the scalar point math, vectorized instructions and the GPU native operations in background. And the best part, we do not have to touch the LLVM IR or the PTX directly. Triton basically handles this entire journey for us. Alright, now that we have understood what is actually happening under the hood, let's now actually run our matrix multiplication kernel. So in this particular code, we have got one script doing two jobs. One is the Triton matrix multiplication and the other one is the PyTorch matrix multiplication using the exact same input matrices. So I have already installed the Triton and the necessary packages in my environment. So let's start running the code. Alright, here are the results. So across all the sizes we have tested, the average torch throughput comes around 9.41 TFLOPS and the average Triton throughput comes around 9.87 TFLOPS, which is giving us an overall average speedup of now 1.9x. Since these numbers are from a CPU setup and Triton is really built to shine on GPUs, the results might look a bit mixed right now. Some matrix sizes, Triton actually wins and some PyTorch wins. But on a properly supported GPU, we should be definitely able to see better performance, especially after the kernel is tuned and warmed up. That said, it is not all sunshine and TFLOPS. Debugging is still GPU kernel debugging, and the JIT makes it tougher than the normal Python. Right now, the Triton's platform supports the strongest on NVIDIA, with AMD and ROCm still improving but not as mature. Also, the first run includes the compilation overhead, so warm-up really matters. And for simple element-wise operation, PyTorch is usually fast enough. Triton actually shines the most when we need custom-fused kernels and performance-critical parts. Video help you to understand about Triton. Drop a like and subscribe to our channel. And comment below if you want to have a live coding session on Triton kernels next. Until then, this is Pranav signing off. And this time, I'll make sure the next upload doesn't take this long. See you in the next one.